Okay, so we often talk about the really big stuff on this show, right? Black holes, galaxies, these vast cosmic distances,
Mm-hmm.
the grand scale.
Exactly. But today, we're going to do the opposite. We're diving into the smallest space imaginable where the most powerful interactions in the entire universe are happening.
And our sources for this deep dive had a perfect name for it.
They really did. They called
Ugh.
it the hidden glue of the cosmos.
That phrasing, it gives you a real sense of the immense responsibility these little particles have.
It does.
Our mission today is pretty straightforward, but I think it's also, profound. We want to understand the strong nuclear force and the particles that carry it, the gluons.
Because if you want to know why atoms don't just, well, dissolve into chaos,
This is it. This is the answer.
and that stability, that structure, that's the core idea for you, the listener. Every single piece of matter you interact with, the chair you're sitting on, the air you're breathing.
Given the structure of your own DNA. Right. It all relies on this constant, powerful operation working flawlessly. It's like a 247 battle happening inside every single atom.
It is. And the sheer power needed to win that battle is, it's just astronomical. We're going to explore why this force isn't just strong. It is demonstrably the most powerful, fundamental force we know of, period.
So to get the solution, we have to start with the problem. Let's begin with that central dilemma inside the atomic nucleus, which, our source material boiled down to a really simple question.
Why doesn't everything just explode?
Exactly. It sounds like a philosophical question, doesn't it?
But it's pure physics, a pure practical physics problem.
Right. So picture the nucleus of an atom. It is unbelievably tiny. I mean, a space a trillion times smaller than a speck of dust.
And inside that incredibly compressed space, you've got protons just jammed together.
Now, anyone who's played with magnets, even as a kid, knows the basic rule of electromagnetism.
Like charges repel.
Like charges repel. And protons are all positively charged. So when you shove a bunch of positive charges into that infinitesimal space, they should just push away from each other with this overwhelming force.
And we're not talking about a gentle push. This repulsion is massive. If you just held two protons a centimeter apart, the force pushing them away would already be enormous.
But you confine them to the scale of a nucleus.
They should absolutely detonate. I mean, the nucleus should be fundamentally unstable. It shouldn't be able to exist for even a millisecond.
That's the paradox. It's like nature has placed this colossal internal time bomb inside every atom in the universe.
And if the rules of electromagnetism were the only rules in the game, every element heavier than hydrogen would just fly apart instantly.
So there has to be something else.
There must be a countervailing force, a completely different law of physics that is powerful enough to not just equal, but completely overwhelm that electrical repulsion.
And that brings us to what our sources called the salvation for the atom.
The gluon.
Even the name is so descriptive, they literally work like glue.
That analogy is a good starting point, but it drastically undersells the, let's say, sophisticated violence required to keep that atom intact.
Okay, sophisticated violence. I like that.
Gluons are the force carriers for the strong nuclear force. They're basically these messenger particles zipping back and forth at the speed of light, constantly transferring energy to bind matter together.
So their whole job is to just overpower that basic rule of repulsion and make sure things stay stuck. But we need to be really specific about what they're sticking together because the sources mentioned two distinct levels this force works on.
That's vital. The strong nuclear force acts on two scales. First, its main job, its foundational job, is internal. We know that protons and neutrons aren't fundamental particles themselves.
Right, they're made of smaller things.
Exactly. They're made of even smaller particles called quarks.
And quarks are the true building blocks. That's as depth as we can go right now, structure-wise.
Precisely. And the gluons are what bind those three individual quarks together inside a single proton or neutron.
Okay, how? How do they do that?
Well, to understand it, we have to go beyond simple positive and negative electric charges and introduce a new idea called color charge.
Color chart. Wait, is that literal? Like, are quarks red and green?
No, it's just a helpful label physicists use. A good analogy is electric charge has two types, right?
Yeah.
Positive and negative.
Yeah.
Color charge has three types. We just call them red, green, and blue. Quarks have a color charge, and the gluons are the agents that carry the force between these colors. They make sure that when quarks combine to form a stable proton, the whole particle is color neutral.
Or white, if you stick with the analogy.
Exactly.
Okay, so gluons are the glue within the glue. They're holding the pieces of the proton together. But this brings up a key question, and this is where that simple sticky glue idea completely breaks down for me.
Go on.
If this force is so incredibly powerful, why don't the quarks just, collapse into an infinitely dense point? And on the flip side, if I try to pull them apart, what happens?
Ah, that is the deep dive insight right there. This is what makes the strong force so unique. Unlike gravity or electromagnetism, which get weaker the farther apart things get.
Yeah, the inverse square law.
Right. The strong nuclear force, mediated by gluons, does the exact opposite.
Wait, it gets stronger when you pull.
Exponentially stronger. It's a phenomenon called asymptotic freedom. When quarks are really close together, the force is actually pretty weak, which is why they don't collapse.
Okay.
But the moment you try to separate them, like pulling apart a piece of taffy,
Uh-huh.
the gluon force intensifies dramatically. It fights back with incredible strength. We call that color confinement.
So if I could somehow grab a proton and try to rip one of its quarks out,
You can't.
the force just becomes insurmountable.
It becomes effectively infinite. It's like stretching a rubber band that suddenly transforms into a solid steel cable. The energy you'd have to put in to pull them apart would eventually become so enormous that the energy itself,
What? It just breaks.
it converts into mass. E equals mc squared. It spontaneously creates a brand new pair of quark-antiquark particles that immediately bond with the ones you were trying to separate. You can never, ever isolate a single quark.
That is truly mind-bending. The gluon isn't just strong, it's like aggressively defensive of the structure it maintains.
It is. And that aggressive defense brings us to the second scale it works on, solving that original problem of binding the protons together in the nucleus.
Right, the repulsion problem.
The force binding the quarks is the fundamental force. But the force holding the protons and neutrons together is what we call a residual force.
Like a leftover effect.
It's a perfect way to put it. Think of it like this. Individual water molecules are electrically neutral, right? But they still stick together through residual forces, like hydrogen bonds.
Okay, I'm with you.
It's similar here. Even though protons and neutrons are color-neutral packages of quarks, the intense gluon fields inside them still leak out a tiny bit. And that residual effect is strong enough to glue the entire nucleus together.
So the electromagnetic repulsion between all those positive protons is immense.
But the residual leaked-out gluon power is even stronger.
It's like a secondary security system that still manages to overpower electricity itself.
It's the ultimate internal security system for all of matter. And that residual force is what stops that atomic time bomb from detonating.
This all sounds incredibly powerful, but we really need to talk about the magnitude. Because this is the moment where the physics stops being just interesting and becomes, well, completely staggering.
This is the real aha moment.
Yeah.
We can't just say the strong nuclear force is strong. Our sources were very clear that we have to emphasize it is the strongest force known in the entire universe.
It just dwarfs the other three fundamental forces.
It's not even in the same league as gravity, electromagnetism, or the weak nuclear force.
Let's give some context here. Let's talk about gravity. Gravity holds the moon in orbit. It keeps our entire solar system together. It defines the structure of galaxies. On a cosmic scale, it is immense.
And yet, if you compare that majestic galaxy-shaping influence to the strong nuclear force inside a single atomic nucleus, the comparison becomes absurd. The sources gave the ratio, and it's shocking.
Go on.
The strong nuclear force is stronger than gravity by a factor of 100 times a billion.
Whoa. Okay, let's sit with that for a second.
It's
100 times a billion. That's a 1 with 40 zeros after it.
It is. I mean, to try and put that into human terms, if gravity were strong enough to lift a single feather,
Yeah.
the strong nuclear force would be powerful enough to lift every skyscraper and every mountain on planet Earth, all at the same time.
That imbalance is almost incomprehensible. So the only reason gravity seems so dominant to us is because it has infinite range.
Exactly. The strong force is the undisputed, unchallenged king, but its kingdom is tiny. It's constrained to the atomic nucleus. Within that tiny sphere, though, its power is absolute.
And the consequence of that power, that's what we see in stars. It's what we harness in nuclear energy.
Absolutely. Fusion and fission are just us releasing a tiny fraction of the stored energy of the strong nuclear force when matter changes state. It shows the incredible binding energy the gluons are exerting, constantly.
Without that profound scale of power, you wouldn't have the energy to create or sustain stars in the first place.
No elements heavier than hydrogen would be possible. This one tiny particle mediates a force that makes everything else possible.
So this astonishing invisible power is operating all the time. Our sources use this wonderful phrase, saying the gluons are working 247 inside every single atom of every single object.
It's not a passive structure. It's a constant, active battle against total disintegration.
And if that constant energy transfer just stopped, if the gluons took a nanosecond off,
The consequence would be total and immediate.
the entire universe as we know it would just cease to exist instantly.
That's the dramatic truth. The sources summarized it perfectly. Without this constant operation, the cosmos would fragment. It would fall apart. Every atom would instantly become a chaotic soup of unbound particles.
All stars, all planets, all mountains, all of us would just revert to a state of absolute formless chaos.
Hmm.
It's truly astonishing, then, that the biggest things in the universe, the stars we see, the cities we live in, they all rely entirely on the smallest things operating flawlessly, moment by moment, with a power that just utterly dwarfs gravity. It really changes your perspective on what stability even is.
It forces you to understand that stability isn't a given. It's not the default state. It's an active achievement. Physics isn't just describing what's there, it's describing the relentless, unseen forces required to keep it there.
And the most important principles aren't found in the vastness of space, but in these microscopic details.
Exactly. Mediated by particles we can never even hope to see.
And I think that is a powerful thought to leave you, the listener, with. Since this incredibly powerful, invisible force is constantly working inside every particle of your body just to prevent complete atomic collapse, what does it mean to live in a universe that is perpetually moments away from disaster, yet at the same time, perfectly stable?
So next time you feel the solid floor under your feet, or you see mountain range in the distance, remember that solidity isn't passive. It's the result of gluons winning a war against electromagnetism 24/7. Which really makes you wonder, what other hidden essential forces are you overlooking in your daily lives? The ones that are silently and relentlessly holding your world together?